Hello friends, welcome again to the week 5. So in this week we will be learning about the metal 3D printing. Till now we have observed the 3D printing process for the polymer based material, for the gel based material. We have seen their standard protocol of operation, and we have seen some of the small case studies to fabricate some of the components. So in this week we will be specifically focused on the 3D printing for the metals, as we know that 70% plus contribution is going towards the metal fabrication, and this is going to be really a game changer for the conventional manufacturing process. It is expected that in coming 5 years the whole subtractive manufacturing may shift to the additive manufacturing with a use of the metal 3D printing part. Like for an example, I came to know that for the let us say the tractor component, which is basically one of the automobile main product, there are around 5000 plus sub assemblies, and which are prepared by different subtractive manufacturing. In coming 5 years this is going to be total manufactured by a metal 3D printing. So you can see this technology as a really a game changer, right? So metal 3D printing, again the additive manufacturing is a revolutionary manufacturing process. Here again, like our previous cases, we are making the component layer by layer using a digital data. Similar to our previous practice, the digital model is sliced into the multiple cross sectional layers. Of course, I need to have a software. N number of open source software are available. So each layer is subsequently sent to the printer, which follows the instruction to deposit and fuse the material according to the design. In typical subtractive manufacturing, where I involve the cutting process for shaping the material, here I am adding layer by layer, just similar to my polymer printing or the gel based printing. Typical complex geometries can be fabricated. uh, I show here one of the most commonly used metal printing, that is called the laser powder bed fusion. So we can see the schematic over here. Basically I put the loose powder at this position. So this is the metallic powder which normally comes in the powder form, varying from 10 micron to 30 microns depending upon the accuracy you want for the final product. Then I have a plunger which basically lift this powder over here. Then there is a roller which basically spread this material over the platform, right? So the material is deposited over here. As a thumb rule, if I put a material, let us say 3 mm, so after the ruler passes over here, so the thickness become 1 mm. Although we have some settings like how much compaction we want, but for normal these type of printer, 3:1 compaction is most commonly used, right? Then I have a laser system and the scanner system through which the laser beam is coming, and it is basically fusing the at the selective location over the powder bed, and I am able to get a 3D printed fabricated part at this platform. You can see the video actually working for one of the powder bed printer, that is known as direct metal laser sintering, that is available in our lab, supplied by a 3D systems company. It's an open source machine. This is a US based manufacturer. So metal additive manufacturing is a, of course, a groundbreaking manufacturing process. Of course, it is revolutionary because I can work up to 1700, 1800 degrees Celsius temperature. We are working with the TI6AL 4V alloys with a melting range up to 1700 degrees Celsius. So I have a precise control of depositing the material layer by layer. So each layer is bonded to the previous layer to create a intricate shape and the complex geometry. So this technology has emerged as a superior alternative for the even for the customized production, and we can construct the complex geometries. We can produce the customized component with a multi-material fabrication facility, and we can eliminate some of the steps required for the assembly of the component, and there is a waste minimization. Specifically, if you are interested in industry 4.0 type activities, IoT based solution, AI based solution, this technology has lot of role to play. Now this is the chamber that I am going to show you. This consists of feeding piston, sintering piston, roller, scraper, heating element, collecting tank, and oxygen analyze sensor. So this is the close view you can see over here. Here is the oxygen analyze sensor. This is the collecting tank. Here the sintering piston will come. From here the feeding piston will come. Then scraper will move. This is the roller, and of course here is the complete heating arrangement. So the laser assembly in this machine consists of a collimator arrangement, a scanner head, there are some lenses and the laser that are being used. So for this particular machine that we have in our place, this is having a 300-watt single mode fiber laser source, work in the range of 420 focal length, flat field f theta lens, that is good enough for us to get a precise layer by layer sintering of the material. So we work in the range of 1070 nanometer wavelength, and at the laser power of 300 watt. The bed size is 140 by 140 by 100 mm, and we have the accuracy up to 20 micron in x and y axis. Now, one of the best thing that is possible with this type of machine is making a functionally graded material. Like you can see over here, the lowest part that you see over here, this is made by aluminum, and here I have a copper plate. So there is hardly any other technology through which I can make these type of the functionally graded material. Similarly, we can have a 316L, that is basically a stainless steel, and on this side you can see I have a this copper tin 10. Then you can think of different combination of functionally graded material. Here in this case the reports are there that nickel titanium, which is basically a nitty lie, specifically 4D application, and on the top the TI6AL 4V has been printed. So that is the beauty of using these type of metal printing process. Now this is typically a fishbone diagram for my laser powder bed fusion. So there are some specific input like laser type, laser power, wavelength, beam profile, spot size, scan spacing, scanning speed, overlapping, then layer thickness, powder shape, powder size, powder flowability, powder density, powder life cycle, powder chemical composition, thermal and metallurgical features, inert gas pressure, substrate geometry. This can actually control final output, which is in the measured in the form of mechanical properties, tribological properties, residual stress, post treatment, different type of surface defects, microstructure, geometry, surface structure, and the porosity. And specifically when I talk about the process, this involves rapid cooling and solidification. So I have to typically consult about the different type of the grain structures. Then dynamics of the melt pool is really important. Surface tension, spatter, absorption, conduction, convection, radiation, diffusion process, these are the inbuilt process involved. So this is typically a complex process which has a similar behavior like to our metal casting and welding. So I have to consider all those aspects. for controlling the output properties in terms of mechanical, tribological, morphological, residual stress type things. Now coming to the commercial available 3D printing process, metal 3D printing is broadly categorized into two types. One is called powder bed fusion and another is called direct energy deposition. Under the powder bed fusion, we have a laser powder bed fusion, electron beam powder bed fusion. Then another DED, I have a powder DED and wire DED. And further, this laser power, we have a SLS, selective laser sintering, selective laser melting, direct metal laser sintering, electron beam melting. Then under DED, I have a direct metal deposition, laser metal deposition, wire arc additive manufacturing. Now, DED is one stage ahead of laser powder bed fusion. Here, the energy requirements are high, but for the small size component, the flexibility with the powder bed fusion are more. But if you are interested in mixing, like the pre-line type thing, we are interested, then DED is going to be a better process. Then coming to the type of the metallic materials that we work on, most commonly titanium, nickel, stainless steel, cobalt, chromium, aluminium, then high entropy alloys are very commonly being used with this type of process. Then there are some specific application like for titanium alloys, of course, for the biomedical application, stainless steel and nickel alloy again for the biomedical application, aluminium alloys for different, lightweight engineering application in aerospace industry, and these type of metallic powders are available commercially, which are normally produced by a process called ultrasonic atomization. So in our place, normally we go for FBI approved metallic powder so that it can be used for actually implantable application. So we have a facility for nickel 625, that is inconel. We have a facility for 174 pH stainless steel. Then we work on titanium alloys, but the machine for this type of thing is an open source and can accommodate any sort of material. Only the constraint is we must work in the range of 10 to 30 micron as regard to the particle size is concerned. Sometime in case of the reused powder, there is a satellite particle formation that is just need to be avoided because that affect the compaction part of the powder bed. Otherwise, the requirement is not very stringent other than the particle size. So here are some of the preparation stages. Like I have the metallic powder, I need to go for the sieve shaking, then the overheating, then going for the printing of the part. This is actually the 3D printing setup that is in our place, provided by 3D system. Then we go for the post treatment and the surface finishing as regard to the component manufacturing is concerned. Now, before I go for printing, because the metallic powder that we use is really costly, so we need to go for the preprint analysis. So the software helps us in understanding the accumulated stress, accumulated heat areas, and boundary distortion. So what we do at our places, we use this 3D system based software, and we go for these type of analysis before actually going for the printing part. The same analysis is also possible in ANSYS platform. If you have a ANSYS based platform, the similar type of data, residual stress, number of strains going for the number of cycles can be done, right? So this is the some effect of the input parameters like the scanning strategy. It has been reported that it has a significant effect on the residual stress, on the microstructure and the mechanical property that we need to do. Like this is very important when we are interested to make some metastructure for typical exotic or the exotic structure for typical 4D applications, right? Then again, for the optimization of metal printer, we can use different strategies. Like this is one schematic for LPBF processing parameters. I can work on laser power, I can work on scanning speed, I can work on hatch spacing, I can work on the powder bed compaction, layer thickness, so that actually affect the printing parameters. As a thumb rule, we use this equation, that is basically controlling the energy density that is given by laser power divided by scanning speed hatch distance and layer thickness. So if you see the manufacturer guidelines, they actually go for the value of the ED. Like for titanium, you have to go for this level of ED for titanium, for aluminium, for copper. So we have a range of ED that can be controlled through the laser power scanning speed, hatch distance, and layer thickness. That helps me in controlling the basically the process, right? So this is one of the example I have put over here. We have fixed the ED, that is the energy density, in joule per mm cube at level 50, 55, and 60. Then build orientation 0 and 90. That is of course really important, because sometimes if you put the component along x-axis, then what is the powder consumed, and if you orient the same component vertically, the consumption of the powder is increased significantly. Then scanning speed is of course and the scanning strategy, that is also very important. So that has been selected in this DOE, and finally a component has been prepared. This is just the overview of the metal printer. So we try to learn about some of the parameters. Now in our coming session, we will see one or two case studies of controlling the process parameters of the metal 3D printer. I hope the information is useful. Please keep watching this from our these two upcoming case studies. It will be really useful for all of us to actually implement this in the field. Thank you.